Good evening and welcome. I'm Rick Reedy, trustee and chairman of the Advisory Committee on Socially Responsible Investing here at BU. It's my pleasure to welcome everybody here. As some of you know, maybe all of you, I don't know, the Advisory Committee on Social Responsible Investing is composed of trustees, faculty, and students, all in equal numbers, and was constituted by the Board of Trustees to be knowledgeable about certain relevant socially responsible investing issues and to advise the board on its policy issues. The committee is currently considering a petition submitted by a group of faculty and students calling on the university to divest from the investment in fossil fuels. As part of our deliberations, we are holding a series of community forums at which recognized experts on subjects relating to climate change and sustainability would offer remarks and respond to questions. The intent is to provide thoughtful insights that inform both the committee as it deliberates, as well as the broader community. This evening's event is the third in a three-part series this semester. Now about our lecturer, we are very pleased and honored that BU's own Professor Anthony Janetos was available to join us tonight. Dr. Janetos is a professor of Earth and Environment in CAS, and he serves as director of the Frederick S. Pardee Center for the Study of the Longer Range Future, which is an interdisciplinary, university-wide research center focused on the evolution of the human condition over periods of decades to centuries. Dr. Janetos has written and spoken widely on the need to understand the scientific, environmental, economic, and policy linkages among the major global environmental issues. In addition to his research interest in the interaction of land systems with human needs and climate change, he has also been an IPCC lead author and coordinating lead author, and has served on multiple National Research Council committees and boards. Dr. Janetos' lecture is titled, as you can see tonight, Climate Change Impacts and Responses in the U.S. and Beyond. I'm looking forward to hearing from him, and now without further ado, Dr. Janetos.
Thanks very much, and thank you for the opportunity to come and talk. My fervent hope is that my voice will last as long as the seminar does, but we'll see. I want to start with a quotation from one of the most distinguished physicists of the 20th century. And what I really want to talk about now are four things this evening. I want to talk about context, which apparently didn't make it onto this particular slide. And really the idea about context is, why is this issue so important? Secondly, I want to talk about what we do know and how do we know it, because that's actually quite important for understanding how this entire issue has evolved. The third thing I want to talk about are implications for the future. Because what I'll talk about before that is what we know today, and try to get across the idea that this is not an issue that depends, the knowledge of which depends completely on mathematical modeling. We're now talking about a phenomenon that is observed, that is consistent with what we know about how the physical world works, and that we actually are beginning to understand in many instances really quite well. And then what I'll finish with is a review of many of the actions that are currently being undertaken, both in the U.S. and to some extent in other countries. And there I will focus primarily on adapting to change. But the first thing I want to show you is a picture of a neighborhood. And the reason for this is that climate change and its consequences really are quality of life issues for all of us. And there are a number of reasons. And one is that these global environmental issues also have immediate local implications. And they're not just implications for today's world, but they're implications that have this long tail, that they'll be important for decades to come. They become quality of life issues not only for residents, but for people who do business in these neighborhoods and for entire regions. And we really don't any longer have the luxury to ignore what facts tell us, or to ignore the experiences of others. And one thing I can't emphasize strongly enough, that this is not an issue of belief. This is not an issue of faith. This is an issue of considered evidence. And lastly, I think that we're at a state now where those of us in the scientific community, of course, are trained to and are driven by a desire to understand better the way the world works. But we are also, I think, particularly for climate change-related issues, we need to be cognizant that what we're also doing in a societal sense is managing risk. So we're doing both at once. We're managing risks as well as seeking to understand the world better. There is a long history of how we know more and more about this issue. For over a quarter of a century in the US, pardon me, the federal government agencies, the science agencies, have collaborated on all fields of climate science. And for the past 15 of those years, the scientists involved in that research have published our best assessments, our best evaluations of the state of science regarding climate change and its impacts in the US. This parallels, in fact, the development of the Intergovernmental Panel on Climate Change, which is the international scientific assessment process, which has involved over 5 separate reports from its very beginning. So it's now it's just finished its 5th round, each one of which involves thousands of scientists around the world, more thousands of reviewers, and is set up to provide the best consensus on the state of knowledge that the scientific community can provide to the policy community. And so let me talk a little bit about where we've been and where we are now in our understanding. And so this is partly a history lesson. The very first of the US national assessments was this document. This was published, this was actually begun during the Clinton administration. It was, unfortunately for those of us who were authors and participants, it was published on the day after the presidential election between Mr. Gore and Mr. Bush. And so the eyes of the nation were not focused on this. We were a little more concerned about who was going to be our next president. But this was then followed by a series of more than 20 individual scientific assessments on particular issues. And this happens to be one that I led on effects of climate change on agriculture, water resources, and biological resources. And then about at the end of the decade, we published a second national assessment, which was a synthesis and a review of all 20 of those topical reports, as well as additional papers in the scientific literature. Just a year ago, in fact, a year ago next Wednesday, we published the third National Climate Assessment, which is a thorough review of the state of science regarding climate change impacts in the United States. So let me share with you first some of the bottom lines of this assessment. So I'll share some of the conclusions before I go into a little bit more of the evidence. So one of them is, and this is a trend that we've seen both in the national assessments, the US assessments, and the international assessments, is that this is no longer a phenomenon that we talk about occurring decades from now. This is a phenomenon that's occurring now, for which we have observations, for which we have evidence that we see happening around us. Secondly, in this country, as well as in, as I'll show you, many countries around the world, we are already feeling the effects of some particular aspects of climate change, in particular in episodes of extreme weather and sea level rise. These cars were not attempting to find that last parking place. This is actually some of the aftermath from Superstorm Sandy. Third, impacts in the US are now apparent in every region of the country and in nearly every sector of the economy about which one might be concerned. But there are many actions that can be taken and that are being taken, both to reduce the prospects of future change in the physical climate system and its impacts, and to prepare for the impacts that we can't avoid. Because the the fact of the matter is that some impacts are now baked into the system. We will not avoid them. We are not avoiding them now, nor will we. So let me move on a little bit to talk about the planet itself. The world is indeed warming. There are numerous independent lines of evidence that show this. And of course, the climate varies naturally. It varies week to week, month to month, season to season, year to year. We have warm years and cold years, wet years and dry years. But this trend of human-driven change is superimposed on that. So of course, we don't see exactly the same effect in every place around the world. If you look at global annual average temperatures, that's what these blue and red bars are. So these are the deviations from the long-term average from the middle of the 19th century in this graph. And so the trend is actually pretty clear. We've seen this long-term rise in annual average temperatures, globally averaged in this case. And along with that is this phenomenon of what we've actually done to the atmosphere. So I've only put the atmospheric concentrations of CO2 on this graph. It's by far the most important greenhouse gas that we've added to the atmosphere. We're up at around 400 parts per million, a concentration in the atmosphere that we haven't seen in tens of thousands of years. So we are essentially outside of the natural range of variation in terms of atmospheric composition. Now, this shows a lot. You see there's lots of individual year-to-year variation. And of course, for a long-term trend, you might not want to pay attention to all of that individual year-to-year variation. And so one way to think about that is, what does this look like if you average it by decade? And to no great surprise, it looks pretty similar. These are also deviations from the long-term average. And one of the really interesting features of this is that for 3 decades in a row, each successive decade has been the warmest decade on average in the instrumental record. Now, one thing that many people, in terms of trying to communicate about this, one thing that many people respond to is, oh, well, you know, the 40s were cold, the 70s were cold, and you can always find in a record like this, where there's lots of individual variation, you can always find periods where the temperature doesn't rise. And so this is one example. I've shamelessly stolen this slide from Richard Alley at Penn State. And so let me go back and show you this again. What you see in this is that there are decades where the decadal average is relatively flat. But when you look at this time series over a substantial period of time, it's actually quite clear what's happening. Is that the state of this system is changing quite substantially over this same time period. Lots of different ways to portray this. If I can make this work, this is a particularly cool one. And again, these are records for individual years, month by month, and you see where the 20th century average is about a third of the way up the graph. And what's happened from about 1958 till now is that each year, each decade, even with lots of variation, has gotten successively warmer. Now, there are many consequences of this. Some of them are simply in the physical climate system. So this is what, for example, has happened to Arctic sea ice. So this is floating ice. So this doesn't affect sea level rise. This is the same as the ice that you'll have in your drinks at the end of the talk. If you just stand there and let it float, the water level in the glass doesn't change. Right, so this is floating. It's not grounded. It's not grounded at all. But what we've seen, and these measurements are taken in late September, which is the period of minimum sea ice. It's the end of the summer, before the Arctic starts to freeze up again for the winter. And we've seen this really extremely rapid decline in the extent of sea ice. Now, these data actually come from satellite data, from several of NASA's and NOAA's satellite missions. And this just depicts the change in this 30-year time period from the middle 80s to just a few years ago. But as I said, this doesn't affect sea level rise. On the other hand, this does. So this is the actual loss in mass of ice from Greenland and Antarctica. These are also satellite data from a very sensitive gravity measurement that a NASA satellite makes, and this is pretty definitive. These are the landed ice caps, and they are losing ice over this roughly decade period of time. This is another example. We now have literally in most places around the world, we've got substantial melting back of glaciers, of landlocked glaciers. These are just a couple of examples. You should go to Glacier National Park before it's formerly Glacier National Park. This is, for example, what's happened to Muir Glacier in about a 60-year period. So these are landscapes that are now essentially irreversibly transformed. And why is this? Well, we have caused this, right? Our activities have actually caused this. If you look, for example, at the emissions of carbon, of CO2 from fossil fuels in the industrial age, this is actually what you see. So from the middle of the 19th century, you get this slow increase in fossil fuel emissions, in carbon emissions, until about World War II. And the industrialization of what are now the OECD economies and the developed world takes off after World War II. And we have this enormous rise in the use of coal, oil, gas, and this little sliver for cement. But it's really the combustion of fossil fuels that has primarily generated this trend. Now, I showed you one graph of CO2 concentrations earlier. This is another way to look at that. This actually goes much further back in time using CO2 measurements from air bubbles and ice cores, which are carefully dated, and the concentrations of the CO2 in the captured atmosphere in the air bubbles is analyzed. The astonishing thing here is how stable the carbon cycle is until you perturb it. Primarily with land cover change, with clearing of forests, and then fossil fuel combustion. And this is typical, it turns out, for most interglacial periods. During glacial periods where there's a tremendous amount of ice on the landscape, CO2 concentrations in the atmosphere are actually much, much lower. But in interglacial periods, such as we're in now, CO2 happily bubbles along at about 280, 285 parts per million, with not a lot of variation. You can look more carefully at these data, and you can see seasonal cycles, and you can calculate the average growth rate in CO2. And using isotopic methods, you can determine how much of that extra CO2 in the atmosphere comes from live carbon, that is, comes from land use change, primarily the clearing of forests for agricultural land, and how much of it comes from fossil fuels. These are data that are now about 4 years out of date. The trend hasn't changed, particularly in the last 4 or 5 years. At this point, about 90% of annual emissions are basically fossil fuel emissions. Around 10% or so comes from net land use change. And we know where the carbon goes. And again, these percentages have been relatively stable over the last couple of decades. For the total amount of carbon extra carbon, right, this is the perturbation, that we put into the atmosphere, about half of it stays in the atmosphere. The other half goes into regrowing forests or goes into the ocean. And you can actually do a budget, right? So the Forest Service has actually done a budget for North America, the Forest Service and EPA, and so you see on the one hand you see this enormous set of sources for fossil fuels, but there are sinks. We have regrowing forests in this country, particularly in the east. We actually have more forest in the U.S. than we did in 1960. We've had a fairly rapid spread in no-till agriculture and better soil management and the Conservation Reserve Program. So we've actually got sinks in both forest systems and cropland systems, and then there's a bunch of very, very small sinks that don't actually add up to much, but the sources overwhelm that. And we now have a pretty good dynamical understanding of how what the physical consequences are in the climate system. In fact, we're now at the point where the dynamics of the climate system, represented here by temperature, cannot be explained by natural variability alone. Right? So in this graph, the observations are the black line. And in a set of model experiments, what's been done is the human factors, aerosols, extra CO2, and so on, have been taken out of the simulation. And when you do that, you get the green line. So this actually works, fairly well for about half the century, and then it deviates. If you put those factors back into the model, so you're now taking into account not only all the natural variability that's in the system, but the way that we perturbed it by our own actions, you actually get a surprisingly good agreement with observations. This is one of the acid tests of any sort of complex modeling. And in this, the climate models actually do pretty well. And what we're seeing as a consequence of that is that impacts are already widespread. This is a pretty typical, so this is actually from the third National Climate Assessment. This is a pretty typical kind of graph for sea level rise. We've thrown in observations in particular from Philadelphia just as an example. It could have been Boston, it could have been Baltimore, could have been New York or Long Island. And along this stretch of the East Coast, what you see are somewhere between, sort of a few inches to a couple of feet of sea level rise per century. Now, that doesn't necessarily sound like much. But the problem with sea level rise is not just the inundation. It's not just filling up the bathtub. The real problem is when you get storms that start to push around all that extra water. The contributions to the sea level rise itself are really quite well understood. You have this melting ice, both from the ice caps and from glaciers. You have thermal expansion of the oceans because water, like most substances, expands when it gets hotter, and they have absorbed an enormous amount of heat over the last century. What's left out of those kinds of calculations is the future of the ice caps near the end of this century. That's a significant unknown. But it's not just there that we see these consequences. If you look, for example, this is an index of water stress that's calculated in this particular case by the U.S. Geological Survey. And what you're seeing is this, particularly in the western part of the U.S., you're seeing these much higher levels of water stress. This is averaged over the last decade. This doesn't include, for example, the latest severe drought in California. We see these kinds of effects also in human systems. There will be data here. So this is what's actually happened to heating demand. This is also nationally, and these are again percent differences over about a 40-year time period. And so during this period of fairly rapidly rising temperatures, what we've actually seen in the wintertime is this national decrease in heating demand. And this is accompanied by a substantial increase in cooling demand. Now these are actually demands on two very different energy sources. In the US, heating demand is largely burning oil, burning gas. It's fossil fuel driven. The cooling demand, which for most of the country is largely a warm season, a spring and summertime phenomenon, is an increasing demand for electricity, however that electricity is generated. A number of states and federal agencies have now started to do vulnerability assessments. This is a map from an analysis that was done by, again, by the U.S. Geological Survey, the states of New Orleans, or excuse me, the states of Louisiana, Alabama, and Texas. I was on the advisory board for this study, and what we did was collect elevation data for all of the transportation infrastructure in this stretch of the Gulf from Houston to Mobile. This blue area are all the places where the elevation above mean sea level is below 4 feet. The storm surge for Katrina was about 20. And this is what Hurricanes Katrina and Rita actually did in terms, in this case, in terms of the offshore energy production. So all those little red dots are either oil or natural gas platforms, or at least they were when the hurricanes went through. Katrina in particular was damaging enough to the offshore oil platforms that it actually caused a national blip for about 3 or 4 months in natural gas supplies nationally before the industry was able to recover. Now we know that the Gulf is particularly vulnerable because at the same time as we're seeing sea level rise, and sea level in the Gulf even rise, the land is actually subsiding quite dramatically and quite rapidly. But this is not just an issue, this kind of vulnerability is not an issue only for the Gulf. We have other parts of the country where we have similar issues. This is a report from the Pacific Institute that basically shows coastal power plants in California that are potentially at risk from sea level rise. If you look back at the physical system itself, there are lots of different patterns to look at where there's some quite substantial changes occurring. This is one example of what's happened with actual observations of precipitation changes in the U.S. These are data from the National Climate Data Center of NOAA. Globally, what you would actually expect is for global precipitation to increase. If you pump more heat into the system, you speed up the hydrologic cycle, you're evaporating more water, it's got to come down somewhere. Regionally, on the other hand, you get these really interesting patterns. And so in this pattern, what we've seen in the U.S. Is this intensification of drought and dryness in the West, and particularly in the Southwest, whereas the Northeast and the U.S. as a whole have actually received more rainfall than over time. On the other hand, not all that rain is really helpful, because at the same time as we've seen this overall increase in rainfall, what we've also seen is an increase in the frequency of heavy storms. So in fact, the Northeast is a particularly interesting example because the frequency of essentially the frequency of severe rainfall events has increased by a factor of about 50% in the Northeast. And so we're in this really kind of interesting cycle of, interesting, depending on your perspective, I suppose, of we have plenty of water in this part of the country, but we don't get it in a very effective way. We're either getting downpours or longer dry periods. I won't read this to you, I promise. I use it only to point out that in the scientific assessments that we've done for every sector that we've looked at and for multiple regions that we've looked at, we've got some very clear summary statements about what we see in the data and what we see in terms of observations in today's world. And what we're beginning to explore is how these systems actually interact. And so there's actually in this latest assessment an entire chapter on the interaction amongst energy, water, and land. And so this is really interesting because what we see is that these issues interact, or that these systems interact in particularly interesting ways. So you actually need water, a predictable supply of water at appropriate temperatures to generate electricity, right? Because you need water to cool thermoelectric power plants. or to cool nuclear plants. If that water is too warm, you have to derate the plants and actually start to dial them down because the water is no longer very efficient to carry heat away, because it's too warm to start with. We've actually started to see this happen during particularly warm or drought periods in both the Southeast, and a couple of years ago in the severe drought that Texas saw, people were actually starting to shut power plants down because of this interaction, because we didn't have a predictable supply of water to cool them off. But we are seeing as well risks sort of throughout other sectors. This is a graph from the first national assessment, the second national assessment, where we looked at two different scenarios for the future and compared them to today. So up in the top left is the period from 1961 to 1979. We used a cutoff date in this analysis of 100 degrees Fahrenheit. The colors represent the number of days in the year that are above 100 degrees. And so the historical data are about what you would expect if you live in Death Valley, if you live in the Central Valley, parts of Texas and Deep South. There are a few days in the summer that get over 100 degrees. In some parts, in the very arid Southwest, there are a lot of days that get over 100 degrees. You can look at a low emissions future in the top right and see actually some substantial changes, particularly through the middle of the continent, which really warms up quite rapidly. The high emission scenario is in a sense sort of a fry an egg on the sidewalk scenario, where you actually spend you may not be able to see it on the bottom, but the far right-hand corner is 120 days. That is 4 months of days that are above 100 degrees Fahrenheit. So we've actually redone this analysis for the third national assessment, and I've pulled out we've used a slightly different cutoff date, 90 degrees Fahrenheit, and I've just pulled out the figure for the Northeast. Again, on the top is historical climate, a low emissions future, and a high emissions future. But these are actually quite substantial changes, and they're changes that affect particularly quality of life in urban situations. And one of the things that we found consistently is this interaction of changes in the climate system and changes in other environmental systems. Air quality is just one example where these are temperature-sensitive reactions. So the formation of ground-level ozone from both anthropogenic and natural emissions actually gets accelerated in a warmer climate. We see all kinds of changes, observe all kinds of changes in a raft of natural systems. Spring, you wouldn't know it this year, but over the past 20 years or so, spring actually arrives in this part of the northern hemisphere about a week and a half to 2 weeks earlier, with a concomitant decrease in snow-covered area and an increase in the length of the frost-free season. And we've seen in individual studies of particularly sensitive species, we've seen what we would have expected to see, what ecologists would expect to see. We see the ranges of these species moving northward or moving upward in elevation. And if the species is particularly sensitive, as is the case for this checker spot butterfly, we actually see extinctions in the southern part of the range. This turns out also to be true for fish in the ocean, where we've got all kinds of range changes. Now, one of the challenges in trying to understand climate impacts is that they almost never occur in isolation. There are always multiple factors that contribute to them. So this is actually one of my, I hesitate to use the word favorite. This little bug is a pine bark beetle. So it's a tiny little beetle. It's native to lodgepole pine forests in western North America. And it's a natural part of the disturbance ecology of these montane forests. The beetles will actually begin to infest old or sick trees. They overwinter as larvae underneath the bark. there's about a half a dozen different species. They have the same basic biology. And they'll go through periodic outbreaks. So what kills these guys off? What stops an outbreak? What stops an outbreak is a consistent stretch of very low temperatures in the winter. Depending on the species, it can be a week of -10 or 10 days of -40, and that just depends on the individual biology. But the story is roughly the same for the whole suite of these little insects, and that's what kills them off. It kills them off as larvae. If the winters don't get cold enough, the larvae overwinter, and the next growing season, you have a much larger base of pests for infestation. The previous largest recorded outbreak in the Western Rockies was about 650,000 hectares. The current outbreaks are in excess of 4 or 5 times that. And so there are places in the Rockies that now look like this. So all those red, this is not New England fall. Those red trees are dead. So they'll keep the needles for about 2 years. The needles turn red when the tree dies, and they'll stay on the tree for about a year, maybe 2, and then they fall off. At that point, this dead tree is now very dry in a highly fire-intensive ecosystem. And this is part of what's driven the really quite rapid increase in both the size, the magnitude, and the frequency of forest fires in the West. This phenomenon is not just in the Rockies, it's gone all the way up into Alaska. This is a slightly different species of bark beetle. There's the years from the early 70s to the mid 80s on the left. The red is where this particular spruce bark beetle infestations were. From the mid 80s to the end, basically the end of the 20th century, this infestation exceeded all previous historical infestations. Now I go back to this very first assessment. In this very first assessment, we actually started to catalog for different regions of the country and different types of ecosystems, either the kinds of effects that we were beginning to see or that we had some expectation of seeing. And so there are lots of figures like this. We put together a very nice figure that if you were able even to read the text around this, what you would see is a lot of very probable type language. This is what we think will happen. This is our best estimate based on our current knowledge. By the time of the second assessment, and even more now for the third, that probabilistic language, future-oriented language, is replaced by this is what we are observing. This is what is happening. And this is what we're actually starting to see. There are things that go bump in the night. And some of these really create major strategic challenges for us. And a lot of this is trying to understand the speed, the magnitude of change, and the potential for irreversibility. Now this may sound like heated rhetoric, but we're starting to see these kinds of changes. This is probably the most well-known example in many coral systems globally. We've had now several episodes of essentially simultaneous die-offs and bleaching of these corals. This is a stress reaction from these organisms that are particularly sensitive to high water temperatures. They're sensitive to other environmental insults as well. And so this is part of the complexity of trying to understand the issue. But other environmental insults, eutrophication, overpollution, overfishing, don't occur simultaneously across the world. This does. And the other one that's really, it's both interesting and a little, and I will just say a little scary from a biological perspective, is actually what's happening to the chemistry of the ocean. Now, this is one of the audiences where you've probably all taken this class or you're about to. So this is just the chemistry of weak acids and bases, right? We should have known this, that as you increase the partial pressure of CO2 in the atmosphere and therefore in the surface ocean, they get more acidic. They lose alkalinity and the ocean gets more acidic than it would otherwise have done. This is sort of how the theory works. This is how the measurements work. So this is from the most recent assessment. These are actually data from Hawaii, and so the graph on the top is sort of the famous Mauna Loa graph. That's what's happened to CO2 in the atmosphere. The other two lines are in situ measurements from surface ocean waters. So the line on the top, with the blue lines, is the trace of the partial pressure of dissolved carbon dioxide in the surface ocean, and the line on the bottom is the declining pH. So unfortunately, the world works exactly like you were taught in physical chemistry as freshmen and sophomores, and we're starting to understand the biological consequences of this. Organisms that build a calcium carbonate skeleton in the open ocean are finding it energetically more difficult to actually extract calcium carbonate from the water column and actually build those limestone skeletons. It's a simple function of chemistry. We don't understand all of the consequences of this, but we are starting to see actual economic impacts in shell fisheries on the West Coast, and actually here in Massachusetts as well. The other thing that we've started to do in these assessments is actually summarize for different regions of the country what some of the key messages and key findings are. So I'll just leave this up for a second. This is primarily for this part of the country. And as much as we're seeing and actually observing impacts now, we also have to recognize that they're projected to increase. So in these assessments, and I'll talk now about the last one, what we've done is we've tried to investigate alternative futures. We can't predict which future we'll be in. This is actually a function of what kinds of decisions about the energy system are made. It's not predictable. We don't know what decisions will be made. But we do understand pretty well the physical consequences of being on one of these alternate paths. So in this case, we've looked at a low emissions future and a higher emissions future. And so, for example, you can look at both past and then projected changes in global mean sea level, and you'll get a picture like this. What's interesting about this, in addition to the projection at the end, which is in part a measure of not only our uncertainty about which climate future we'll have, but a measure of the scientific uncertainty and some of the complicated physical processes of how ice caps work, is this smooth transition from a whole host of proxy records to tide gauge data to satellite data, which is, so even as the measurement technology changes, you have continuity in what you learn. To date, I focused on the US situation. This international process has led to strikingly similar conclusions. At the same time as we published the National Climate Assessment for the US, excuse me, the IPCC published its Working Group 2 volume. This is the volume that looks at impacts, adaptation, and vulnerability. And one of the really interesting summary figures is this one. And in this, each icon represents a sampling of the scientific literature for observed consequences of change in the climate system. Which icon you have, the little snowflakes for glaciers, snow and ice, little droplets of water for the water system. Fish is pretty obvious. There's a little tractor in here somewhere for agricultural impacts. The point is, and the degree to which they're colored in tells you whether the impact is large or small. The real point here is that there's nowhere you can go where there's not something to say. So, and this is a process that has involved thousands of scientists, tens of thousands of papers in the literature. And what we're seeing is this astonishing array and diversity of effects around the world. Now, there are uncertainties in the science. This is undeniable. Climate impact studies typically can suffer from three very big ones. one I've already mentioned. There are relatively few examples where the phenomenon is only the result of climate change. There are some, melting ice, for example. In most cases, particularly for ecological resources, there are other factors that are also important. If they're clearly driven by change in the climate system, for example, think about the bark beetles, that's not exactly the same as saying that they can be attributed to human-caused climate change. But we now have a growing literature that looks at the probabilities of changes in the physical climate system between an unperturbed system and the system we currently see. And those studies, whether they're applied to drought, to storms, to heat waves, consistently have shown that the likelihood of changes as large and as rapid as the ones we've seen are the probability that that's happened by chance, that it's simply natural variation at this point, are beginning to be vanishingly small. Impact studies can also take a long time. Some of these changes take a long time to rise out of this sort of morass of ecological noise, and that can be a challenge, but they always tell us something important about risk. They don't tell us what to do. So let me talk a little bit about what we looked at in the National Climate Assessment about what to do. So this is one response. I don't recommend it, but it made for a really pretty funny newspaper cartoon. There are opportunities to reduce future warming by reducing greenhouse gas emissions or increasing CO2 uptake. There are also actions to take to prepare for impacts that are already, in a sense, baked into the system. And some of these are already underway. For the first time in the US assessments, we actually had a chapter on mitigation, on trying to look at the underlying science and economics of reducing greenhouse gas emissions. It is important to recognize that for the next century at least, and largely longer, the climate we will get is almost entirely dependent, except perhaps for black swan events, on what we do. It's dependent on emissions levels. There are long spreads of geological time during which Earth's climate has changed dramatically. Those are they're true, and they are nearly irrelevant to the issue at hand. Right? The climate we get over the next century is largely dependent on what we do. This is by now a pretty straightforwardly accepted conclusion of the scientific community. In this chapter, which I had the pleasure of leading along with Jake Jacoby from MIT, I'll just share a couple of the key messages. And one is something you've already seen, but you might not have thought about, is that CO2 actually cycles through the atmosphere, and it gets removed from the atmosphere by natural processes at a rate that's roughly half the current rate of emissions from human activities. And this has been true for quite a long while. What that means for mitigation, though, is that if all you did was stabilize emissions, atmospheric concentrations of CO2 won't go down. Their rate of increase will stabilize, but they will continue to go up. The same is true for other long-lived greenhouse gases, chlorofluorocarbons, hydrochlorofluorocarbons, nitrous oxide. Methane's probably the exception. The methane lifetime is relatively short, and so we could expect to see effects pretty quickly if one were to focus on methane. We can talk more about mitigation in the Q&A if you want. But the other action, and one that I will spend a little more time on, is adaptation. Because we're seeing effects now, we are by definition adapting to them. Adaptation does require significant thought and maybe a little more preparation than we see here. There is so some of you are too young to know what that is a reference to, aren't you? This is the one TV show my mother wouldn't let me watch, except when we snuck it. So there is lots of local action. There are lots of local action plans from municipalities, from states. Boston happens to be a particularly interesting example. This is a poster from a major conference that we did here in this room, jointly between the Initiative on Cities and the Pardee Center, where we brought together the scientific community, the political decision-making community, the public community, developers in the private sector, and NGOs to talk about potential for partnerships. Boston is now in the third edition of its own climate action plan. And it's a really interesting document. In the plan, they focused on 5 different priorities. Some of them are about reducing greenhouse gas emissions and energy efficiency and energy use. But some of them are about preparing Boston for the impacts of change and trying to think through carefully what one would actually have to do, particularly for those areas of Boston that are vulnerable to sea level rise and storm surge. If you look across the country, there are climate adaptation plans in a lot of different states, perhaps not surprisingly, states that have an extensive coastline. And now, by executive order, every federal agency is now in the process of drafting a sustainability plan. And again, by executive order, every one of those sustainability plans excuse me, has to say something about how that agency is preparing for climate change and trying to adapt to climate change's effects on their operations. What we don't know very much about is how effective these plans will be. They are plans more than actions, and you have this challenge of developing what we call a counterfactual, and that is, what would have happened if this plan were not in place? Right? Which is a difficult concept and a difficult sort of a calculation to do. But part of the reason that we don't know, there are two additional reasons we don't know that much about effectiveness yet. And one is that there is academic knowledge on climate adaptation that's not yet penetrated into private and public institutions. But the flip side is also true. There's private and public experience that's not yet penetrated academia. And so we have, I think, a challenge of how we share knowledge between academe and the world outside of academe in a way that actually enhances the ability to make decisions. So after all this, where are we headed? For the U.S., the U.S. Global Change Program, the collection of agencies that collaborate on climate change science, are actually required by law, by their organic legislation, to produce a new scientific assessment every 4 years. Future assessments are going to need to do several things. And one is that they need to continue to evaluate where our scientific knowledge actually is. What do we know that's different than we knew the time before? How much better are the models that we got? Observations that have changed over time. And that need, I think, will never actually go away. But at the same time, we need to keep track now of a new set of features, and this is more in the realm of social science, which are progress on how we respond. What are we actually doing, both to adapt to change or to try to head change off? The future is always uncertain. Somebody must be studying the end of the Cretaceous extinction. It just says, what do you want to bet I can hit that thing with a rock? But at the same time, you need to keep your eye on the ball. So the sign has sharp edges, but if you read all the way to the bottom, it says the bridge is out ahead. There are continuing research challenges. Impacts are still emerging from the noise. We have seen some entirely new issues that we hadn't anticipated, like ocean acidification, that have arisen. We have this challenge in the underlying science of trying to understand multiple stresses. In particular, natural resources and other sectors depend on a whole host of factors, including our own choice, societal choices and demand for services, as well as changes in the climate system. So the study of trade-offs and tipping points turns out to be enormously important. And these are challenging. We're much better at identifying thresholds at tipping points after the fact than predicting where they're going to occur. And the adaptation challenge is hardly begun to be addressed. Which systems, which sectors are amenable to adaptation, and at what cost? So let me just finish with a few thoughts. We are clearly seeing the consequences of changes in the climate system. We don't typically use in the scientific community this phrase settled science. It's not a concept that resonates with most scientists. On the other hand, there's a lot of what we do know that is simply not in serious question. We have a very challenging problem, on the other hand, of communicating what we do know. And we need to acknowledge in this issue that the world's not waiting while we sort out the things that we're not so sure about. We are indeed, I think, managing risk as well as seeking to understand the world better, and this is a challenge for most of us. It's the epitome of trying to be useful at the same time as we're trying to be interesting. Thank you.
So you'll take some questions.
I'm happy to.
Great, we got time for some questions, but we will need you to go to the microphones. We are recording this for the web, and we need to get your audio. So just go right to a microphone, come on up and ask your question.
Thank you for a very informative talk. Much of the basic science of global warming has already been established in the 1960s, 70s, just the basic tenets of anthropogenic warming due to the rise of CO2 in the atmosphere. But what we haven't seen was deeply committed and meaningful political will to dramatically address this growing problem. Much of it has been due to obstruction by the fossil fuel industry and political powers that are interested in the status quo. More recently, in recent decades, much of the fossil fuel industry has backed groups that have obfuscated the science and planted doubt within the public and within the political sphere, such as the Heartland Institute, American Enterprise Institute, Cato Institute, George Marshall Institute, which I'm sure you're familiar with, that has supposedly are providing this counterbalance science to experts like you and the IPCC. Only recently, the SRI committee has put out, I don't know if you've seen this, a webpage that have cited some of these groups. So I was wondering what, if you saw this, what was your response to this, and the role of these obfuscating political and fossil fuel powers in obstructing meaningful progress on this?
So one of the really interesting features of this phenomenon is where, and we look at some of this, not the political aspects, but we look at some of this issue of where there's experimentation of mitigation and where there's not. So globally, there's a lot of experimentation with mitigation. There are carbon markets in the EU, which have been variably effective. There are internal programs to raise the efficiency with which efficiency of each unit of GDP in China. In the US, where we see lots of, in a sense, policy experimentation is amongst states and regions. Right? So California has a really interesting program. The Northeast states through RGGI have got essentially a regional trading program. Those are essentially built on the success of sulfur trading in acid rain. So we've known the principles of how to use markets to get economically effective trading programs actually for quite a long while. Where we haven't seen is that same sort of experimentation at the federal level. Now, I'm not a big, I recognize the challenges with some of the some of the groups that you mentioned. Some of this is, I think, my personal opinion is it's political theater. You know, not the IPCC it has no, it essentially has no scientific bona fides at all. But I actually think that to blame them only is naive. This is harder than the Montreal Protocol. This is harder than acid rain. To really get carbon emissions out of the energy system is a challenge the likes of which we have never seen in this century. It will not be easy, and it will not be fast, and it will not be free. And you know, typically, at least in the US system, you're looking at spans of decades before there's enough political consensus on a national level to do something really hard. Right? The Clean Air Act took a long time. You know, it took from the late 50s, when the issues surrounding air pollution first arose, to 1972 and the creation of EPA. You know, we forget that EPA has only, I can say this because I'm a lot older than that, only been around for 40-something years. It's not a long time, and it took from 1972 to 1990 before we actually figured out how to amend it. You know, for an issue that, in this case, primarily for sulfur emissions, which we had known for a very long time were doing a substantial amount of environmental damage. This is not I don't say this to offer an excuse. I say this to offer a perspective that we are asking these systems to do something that's really difficult to do, that requires investments in technology, that requires capital, and that requires a degree of public support that that is often difficult to get.
In the slide that you showed of the sources and sinks of the carbon dioxide, the sources, the fossil fuels, just dwarf the sinks. And I was wondering if there are scenarios where the sinks can be scaled up to make a significant contribution of absorbing some of this carbon dioxide.
So the one that's typically, there are two that are typically talked about. One is how much carbon can we get into soils through better soil management, and the other one is reforestation. So slowing deforestation and increasing reforestation is actually a pretty active program. It's one of the few places in the international scene where there's been a lot of traction. And part of that is because some of the big tropical countries have seen it in their interest to slow, for their own national purposes, to slow deforestation rates. It's hard to do. So Brazil went through a long period where their rates of loss of forests in the Amazon actually came down quite dramatically. They've ticked up the last few years. Enforcement is hard, and there are powerful forces in both directions. But the challenge is that, and this is where I think this is sort of analysis of trade-offs really does have to be done. The big challenge is we actually looked at this in a separate environmental assessment called the Millennium Ecosystem Assessment. For the period of the 1980s, for example, the loss of tropical forests was pretty much a one-to-one swap for agriculture. Right? So, I mean, tropical forests at least were being cut down to plant crops. The big challenge is that we're going to add 3 billion more people to this world. And so through some combination of intensification of existing agricultural lands and conversion, we got to figure out how to feed somewhere between 9 and 10 billion people. Now, the other problem is that you could probably, even if you replanted all the area in forest that we lost, say, since 1980, it's not enough to make a big dent in current CO2 concentrations. And so that's just arithmetic.
I'd like to go back to a question that was asked earlier and ask it a slightly different way. So if you look at James Hansen's article, he was the lead author of the PLOS One article in 2013. And currently, our production of CO2 per year in the world is increasing by 3% approximately. And he concludes in that article that very quickly we have to change that 3% increase in CO2 production per year to a 6% decrease in CO2 per year in order to keep the temperature rise under about 2 degrees centigrade. And you know, it seems pretty reasonable to me. If you look around the world and sort of say, well, is that possible? And the answer is, if you look at Germany, for example, Germany is much more dependent upon renewables than we are at this point. You know, their figures like 30% renewables. They're decreasing their CO2 output by something like approaching 10% per year. Their goal is to get onto renewables totally by 2050. They probably won't make it entirely, but you know, they're really doing it. And so it can be done. And so the question is, well, why isn't it happening in the United States? And you talk as if, your answer was as if, oh, it's just hard to figure this out and get things moving. The deeper analysis is that there are groups that are trying to make the change and become more like Germany. And there are groups that are trying to prevent the change from happening and who are funding an effort to obfuscate all of the realities that you were just talking about there. And so we have 97% of climate scientists who agree with what you talk about, and less than 50% of the US Congress who agrees with what you just talked about. In a rational world, there would be 97% of the US Congress that believed what climate change did. So there's some force that is preventing the US Congress from having the same mindset as rational scientists. And that's not just, well, people just haven't figured it out yet or something like that. There's actually a force that is actively trying to prevent people from understanding the truth. It was raised earlier here. And that would be the people who want to continue to see that 3% increase in fossil fuel burning per year. And that would be the fossil fuel industry. And we can go through, well, how did they fund the George C. Marshall Institute? And what is the George C. Marshall Institute? How has it contributed to the wisdom of the situation with fossil fuels? And so this is, I'm talking too long here, I recognize, but I am getting to something. We're talking about divestment here, and that's really the bottom line. And the question is, in a situation where not enough people are responding to the needs of this crisis, what can you do? And people need to speak up. And I would contend that the single most important statement that Boston University could make to the world and to the US government that it thinks more needs to be done. The single strongest statement that it could be made in this crisis situation would be divestment. And so I'm going to ask you, what do you think the single strongest statement would be that Boston University could make to try to reverse this crisis that you've just spent time discussing here?
So I'm going to respond in a couple of ways. And number one is, and I don't mean this to sound critical. You haven't told me anything I didn't already know, right? Everybody who's worked on any of these scientific assessments has, at a minimum, a set of emails, postcards, and letters that we will never show our mothers, right? And we weren't trained to do this. I mean, this is. There is a virulence in the in this debate that is unlike anything I've ever seen in environmental science and policy. It's really quite extraordinary, and as far as I can figure out, unprecedented. The second part of this is that the fact that there are groups who are literally trying to obfuscate, lie, muddy the issue, doesn't make it easy to solve. Now, there's no magic in identifying what a suite of solutions actually looks like. There's also no silver bullet, right? There's no one thing that people can do. There is a whole menu of things that would make sense. There's an enormous policy and economic literature on this. It's reviewed exhaustively in the third volume, for example, of IPCC. We've known this calculation of if you want to have at least a 50% chance of staying under 2 degrees warming by the end of the century, you have to peak and decline emissions by about 2050. And we are nowhere close to being able to do that. If you were to look at the mitigation chapter that Jake and I led, you would see a pretty strong statement that there's no indication that we're on that path, right? Just none. So that's a huge challenge. The second part of that challenge, and the institute that I headed before I came to BU did a lot of analysis on this, is that those conclusions are extraordinarily sensitive to where emissions start to bend, right? And so obviously global solutions are better than piecemeal solutions. And leaving big players out until very late in the game essentially guarantees that you won't, for example, stay under this 2 degree C target. Now, where the 2 degree C target came from is a complicated story in itself. It's not a scientific number, right? It's a value judgment. So it's a value judgment that's partly informed by science, partly informed by a whole host of other things. I'm not going to answer what I think the trustees should do. All right? They're charged with that. They're going to have to wrestle with that. This is, when I look at the principles that they're working under, on the other hand, they seem to me to be the sensible principles. Where does the university risk its, is there any sense for any of these kinds of issues? Does it risk its reputation as a place to foster free and open debate? Does the notion of irreversible or socially unacceptable harm outweigh other considerations, which at least I've interpreted as, are you on the right side of history? And that's my sound bite of that. So I think this is not, any one university or investment fund making a decision is in fact a symbolic gesture. And so one of the questions is, does it meet these sensible criteria, and is it the right kind of it's a political statement, and is it the right kind of political statement that the trustees are comfortable doing it?
Are there areas of inhabited land that will inevitably be covered in water within the next century or so, no matter what we do about it?
Almost certainly. Many of the small island states in the South Pacific some of them are low enough that they're actually in serious danger of essentially disappearing.
So what do you think will be the ramifications of that?
Well, that's really hard to know, right? We already have examples. Well, one thing is people will have to relocate. There's no turning back on that. The world's not going to cool down. Even if there were really dramatic reductions in emissions, there's an enormous amount of heat stored in the ocean. So we're going to continue to have this thermal expansion of surface waters for quite a while. Those people need somewhere to go. And so I think that creates, in a sense, sort of a slow motion humanitarian crisis that really is going to have to be addressed. We have, what's interesting about this is that this is also one of the phenomena that, for example, the intelligence community is really worried about. So there are now a series of reports, about a half a dozen reports, that have come out of various parts of the U.S. intelligence community. And this issue of dislocations from either climate-associated natural disasters, big storms, flooding, or inundation, or the results of persistent drought. This is one of the big issues that they worry about. The world's not empty. And so, if we actually have mobilization of very large numbers of essentially environmental refugees, where are they going? Who's already there? And what kind of, is that a serious enough issue to actually lead to destabilization of states? So that's certainly one of their concerns. We have examples here in this country of, in a sense, population-level responses to what are essentially environmental disasters that are really quite challenging. New Orleans is a much smaller city in terms of population than it was before Katrina. It's about 25% smaller. People aren't going back. And we don't quite know how to think about that. Sorry.
All right, so we're going to do this question, and these will be the last two questions over here.
I'm just hoping to kind of get your opinion. I'm really interested about this effectiveness piece of sort of mitigation and sort of intervention. And this is just sort of ideology, I guess, thinking. Is there anything that we're doing now that's in place now that you can say, in your opinion, or definitively, that is effective, or that is there are sort of any technologies or any actions that are ongoing that have proven to be effective, or that if increased or if invested in will make a really big difference in the short term, kind of not owing that policy piece, not factoring in that component of large-scale sort of U.S. decision-making?
On the side of adaptation decision-making, we've seen lots of examples where it's pretty clear that some things have been effective. Even here in Boston, when the Deer Island water treatment plant was rebuilt, whenever it was, a decade ago, longer, 15 years ago, something like that. It actually was built about 5 feet higher than the original plans. That's a pretty effective adaptation, sort of before-the-fact adaptation against the expectation of rising sea levels. When you do something like that early in the planning process, it can be quite inexpensive. It's just a little more concrete that they poured. There's all kinds of in the sea level rise conference that we did here last fall, we heard from a number of the Boston area developers about technological things that they were doing. So one of the things that was going on there, for example, was for new development, the city tries to work, the city and I guess the redevelopment board tries to work with the developers to put all the mechanical and electrical materials on the roof. Typically, you'd put them in the basement and get them out of the way. That doesn't work so great if you've got floods. So you put them on the roof, and really what you use the underground for, aside from parking, is that's where you put the extra water, and you kind of pump it out at your leisure because you still have power. So that's actually quite clever, as long as you do it when you put the building up. If you had to retrofit, that would be a real challenge. And so one of the big challenges, even in adaptation, is how do you optimize the normal cycle of maintenance and replacement that every institution has to think about, except for perhaps the MBTA, with with preparing for a physically different world. Because the big challenge is that the world that we've seen, that we've experienced, which is traditionally how we think about the future, is, at least for aspects of the physical climate system, is no longer a the most effective guide to what the future will hold. And so this is hard because it means you have to think about, it's not exactly predictable, so you have to think about scenario planning, and you have to think about what your tolerance for risk and loss actually is. But I think there are a number of examples. On the mitigation side, we actually go through quite a number of these in our chapter in the National Climate Assessment. Many of them are actions that are taken for other reasons, right? So it turns out, for example, that new CAFE standards, automobile fleet efficiency standards, have a fairly dramatic effect on CO2 emissions because the transportation sector is about 1/3 of US emissions. You know, the switch to natural gas, this large-scale switch to natural gas, has actually, for a while at least, actually reduced US emissions to the effect that CO2 emissions actually declined for a while, and it wasn't just due to the recession. You know, that was actually spurred simply by market forces. You know, now, will that last? It's really hard to know if that will last. But we do have examples where there are, on both sides, on both adaptation and mitigation sides, that we've got examples of fairly rapid change, sometimes on scales that matter.
First, thanks for a wonderful, illuminating talk, although somewhat disturbing. I want to ask about a carbon tax. It seems like that'd be a great way to both deter global warming by taxing things that pollute and cause greenhouse gases, but it could also be used to, on the one hand, you could offset the effects of the tax by providing an income tax reduction, but you could also use the proceeds from a carbon tax to promote things that are greenhouse friendly, like subsidies for electric cars.
There are lots of proposals, there are
solar
lots
panels.
of policy proposals like that.
What would it take to get a carbon tax going?
I haven't got the slightest idea how to answer that question. There are lots of proposals. There are lots of proposals like that. Many of my colleagues in the economics community, there's sort of a split of opinion between, you know, sort of a cap and trade type regime or a carbon tax. You know, the benefits of a tax is that we know how to administer taxes. Doing a carbon trading regime is hard, right? And you know, so the EU experience is instructive in that respect. On the other hand, we do know how to do trading regimes for other environmental issues like sulfur. So I think you know, I mean, I think one of the big challenges to any kind of proposal like that is not so much the technical aspects of the proposal as the rhetoric that accompanies it.
Final question.
So you mentioned that divestment may simply be a symbolic gesture, but is there something else that BU can do that would be a substantial gesture? For example, you know, most of us in Boston this winter have been paying 22.5 cents per kilowatt hour, which I think is the highest in the continental U.S. So how about something like a PPA with a solar farm or green roofs or something like that?
So we have the lead for BU's sustainability program here in the audience. BU's doing a lot. You know, BU's doing a lot of substantive things in terms of reducing waste, in terms of increasing end-use energy efficiency. I think we met the CO2 goals 5 years early. Dennis, go to a microphone so it gets recorded. So there's actually quite a lot being done on campus. So.
That's my favorite question tonight. We've reduced our greenhouse gas emissions by 25%, meeting our 2020 goal last year. We have a long way to go. 25% isn't enough. And what we're doing is we're analyzing right now how we have a feasibility study currently underway to see how much we can maximize solar on our roofs. And there are lots of variables that make that doable or not doable. So technical challenges, electrical and so on. I won't go into the details. But within the next few months, we will have a plan on how to get renewable energy on our buildings on campus, as well as we're exploring large-scale off-site renewable energy through power purchase agreements. And we hosted on Friday the Green Ribbon Commission, a study group to look at what we can do collectively and really get Boston on the map for renewable energy. This is very much in an early phase. So, I don't know what the outcome will be, but I'm very excited about where the conversations are right now, and hopefully we'll have something really positive to report soon.
Thank you, Dennis.
Thanks.
Great, thanks.
Okay, thank you, Tony. That was fantastic, quite illuminating, and I certainly learned a lot myself. I think when the committee originally sat down and discussed this particular issue, one of the things I communicated to them was that even if we could get this issue sailed through our committee, through the chairman of the board, through the executive committee, on the docket at a trustee meeting and voted to divest, even if that were to occur instantly, which by no means would be the case. There's a lot of education that occurs throughout the trustees, and I think this talks like this, which they'll all look at, will help. I said to the committee, I said, that wouldn't be enough. We really wouldn't have, I don't want to be dramatic about this, changed the world. We wouldn't really have done that much. We have made a political statement, maybe. We're certainly not doing anything that would have any major economic impact. So one of the other reasons that I want to do this, and we want to do a few more of these, is I would love someday to have 500 people here, to have students, and I'm going to pick on the students for a moment, but the trustees are the same way. It's easy when you're voting, when they hand you a ballot and you're voting, for some student government, and there's a little box at the bottom that says, do you agree that BU should divest? And, a bunch of people are going to check that. But they're not going to do anything more about it. They're not going to learn about it. They're not going to come to these, they're not going to think about it. They're not going to become an ambassador throughout not just the university, but throughout their real lives and all that, to help actually make a big change. So I think one of the reasons I think these meetings are important, and I hope as we have a few more that they get bigger and bigger and bigger, that everybody not only learns, not only we, the trustees, learn from this and can make an informed decision, but also we can all be more learned and go out and be ambassadors to our families, to our communities, to our neighbors, whatever it might be, and teach them what it is that they need to know to be able to affect ultimately political change, because in the end it really is a political issue because we're asking so much from so many people to make this change. So without that, I'm staying. Anybody want to talk to me, ask me more questions, I'll be right out here. I believe there are refreshments right out here. We're adjourned now, so please join us. Thank you.